Everything a computer processes is ultimately a logical abstraction. Documents, videos, and complex software are all reduced to a system of binary ones and zeros. Inside the machine, that logic works perfectly. But when that data attempts to leave the computer to travel across a network, those abstract bits hit a physical barrier at the network port. A digital bit does not natively exist in the physical world. A copper wire has no concept of binary logic. It only reacts to physical phenomena like electrical voltage. To bridge the gap between mathematical logic and physical reality, networks rely on the OSI Physical Layer. It provides the standardized methods to translate abstract information into raw physical energy. This diagram outlines a transmission's life cycle. The physical layer accepts a complete data link frame, encodes those bits into signals like electrical pulses or light waves, and transmits them. At the destination, these individual signals are retrieved and decoded back into a digital frame. The physical layer is the standardized system of engineering required to ensure abstract digital logic can survive the chaotic physical world. The success of this translation depends on exactly how a computer manipulates electricity to represent a message. The first process is signaling. Signaling is the physical generation of energy on the media. On a copper cable, a network interface card generates rapid, pulsing changes in voltage to represent individual bits. This graph maps signaling, showing voltage over time. The transmitter creates a square wave, alternating current between high and low states. A high voltage level represents a binary 1, and a lower threshold represents a 0. However, basic signaling has a technical flaw. If a computer sends a long string of consecutive zeros, the voltage remains low and flat. Without constant fluctuations, the receiving computer's internal clock can drift, making it impossible to tell exactly where one bit ends and the next begins. To solve this timing issue, the physical layer applies encoding. Encoding is a predefined pattern applied to the signal, so both the sender and receiver stay perfectly synchronized. The Manchester encoding graph illustrates a classic solution used in early Ethernet. It doesn't rely on static voltage. Instead, it uses a mandatory transition mid-bit. A low to high transition is a 1, and high to low is a 0. The electrical movement itself defines the data, forcing continuous resynchronization. Signaling generates the raw physical energy to cross the wire, while encoding provides the grammatical structure that makes that energy intelligible to the machine. Once a reliable signal is established, the next engineering challenge is measuring the volume and speed of those encoded signals. We define this capacity as bandwidth, the theoretical maximum amount of data that a physical medium can carry in a given amount of time. This illustration compares bandwidth terminology. The pipe's total diameter represents bandwidth, the maximum potential capacity. The actual measured flow of bits is throughput, which is always lower due to resistance and interference. Finally, subtracting protocol overhead from throughput leaves goodput, the usable payload data successfully delivered. Every layer of the network requires its own control information and error-checking bits. This tax on the connection constantly consumes a portion of the overall capacity. Because of physical interference and protocol overhead, a 1 gigabit link never delivers 1 gigabit of usable file data to the end user. The medium carrying the vast majority of this local traffic is copper cabling. Copper is the industry standard, offering low electrical resistance. It is highly cost-effective and flexible for complex installations. However, copper signals are sensitive to environmental noise. Fluorescent lights and electric motors generate electromagnetic interference, which can distort the timing and voltage of the signal. But an even more frequent threat comes from within the cable itself, through a phenomenon known as crosstalk. This diagram illustrates the mechanism of crosstalk. When electrical current flows through a wire, it generates a small magnetic field. If a second wire runs parallel next to it, that magnetic field induces an electrical disturbance on the neighboring wire, corrupting the signal. The engineering challenge is protecting the data from this magnetic interference without wrapping every cable in heavy, expensive metal shielding. The solution relies on a geometric principle rather than physical armor. This is the basis of unshielded twisted pair, or UTP cabling. UTP exploits the physics of cancellation. When two oppositely charged wires are twisted together, their magnetic fields are forced into opposition. They cancel each other out, which neutralizes internal crosstalk and blocks external interference. Inside this UTP cable, 4 unshielded copper pairs are twisted together. To prevent them from aligning and causing crosstalk, engineering standards require varying twist rates. Notice how the blue pair is wound noticeably tighter than the orange pair, ensuring their magnetic fields never permanently align. UTP works by manipulating the physical geometry of the copper, protecting fragile digital signals from a noisy world using nothing but precise design. While UTP's cancellation effect is effective for most networks, industrial environments with heavy machinery sometimes require more robust protection. This shows common copper media. When geometric twisting is insufficient, designers use shielded twisted pair and coaxial cables. STP wraps each pair in a foil shield, and coaxial encases its central conductor in a dense metallic braid. This shielding requires proper grounding at the connector to function. Without a path to ground, the metal shield acts as an antenna, picking up unwanted radio signals and destroying the data inside. Because shielding adds cost and weight, UTP remains the standard for the majority of network installations. Regardless of the cabling used, the physical layer's task is complete the moment that electrical wave hits the destination port. In a fraction of a millisecond, the receiving hardware reads the voltage transitions and decodes that physical energy back into a digital frame of ones and zeros. The physical layer is the standardized orchestration of electrical encoding and geometric design required to bridge the gap between digital logic and physical reality.